the exam on Thursday, I think it would be a good idea to start the exam. I don't know how I do to make this so it doesn't move away. Oh well. The exam on Thursday, right? Is the first three chapters. So you have had a quiz already on chapter 1, chapter 2. The only difference is that there will be a couple of problems, or maybe just one per section. So for sure, a problem to convert units, a problem in kinematics, maybe to describe a position versus time graph, okay, that we did in chapter 1. Chapter 2 is about forces, friction, and Newton's laws. So very descriptive. I might ask a question on 2 using like calculate the acceleration given the force, or the addition of forces, you know, if you have friction. So forces diagram, that needs to be, you need to study that. I'll see if I can do a small review right now on that. And chapter 3 is basically what we did last class, plus finishing today on potential elastic energy and then application of conservation of energy. I will talk a little bit about the work energy theorem, but I think it would be a good idea if we focus on the conservation of energy and how we can use it for problems, maybe a couple of problems. The roller coaster especially. But then the rest is just application, no? Giving the force, giving the distance, find the work. I uploaded, and it's a good idea. I know it's extra credit, but it's kind of enrichment for physics. If you guys attempt the problems that I put every week. So I put the week 4. Let's check this. Okay, so I uploaded this, and I like it because it has quite a few problems about finding work, conservation of energy. So maybe we can do this today. And then collisions, right? Only 10 problems, not a lot. All right. So before we go into that, I think we should agree on a time where you guys should be logging in for your exam. Personally, I think it will be better if you have as much time as possible, but it depends if you have another class before this, or if you have like an appointment or something. So my idea would be to start the exam at 3:15, so you are all set, and then I can upload the exam and you can start working on it. And I think we can extend that time until 5. So will that be okay? I mean, you don't have to, but that will help a lot for time-wise.
It sounds good.
Yeah.
What was that?
You said
It
if it was
sounds
okay, I said yeah.
It's okay? All right. So I will be logging, it's a Thursday, right? Thursday, yeah. I will be logging in around 3:05, 3:10, and we will start and we're uploading the exam. Make sure that you are set. You need to have your cameras on just for attendance purposes. 3, 4, 5 today, right? How many we have? We have 5. And then we can start with the exam. I think that would be a good idea. All right, that's good. And then that means that next week we will start with chapter 4, which is the physics of matter. Don't think, I know that I haven't put all the slides yet here, but I will be doing that during the weekend, the long weekend. But besides the recordings, I have to update. I have to put chapter 5, 6, 7. All right. So we will be closing chapter 3 today. Let's take a look. Let's record what we did last class very quickly. Collisions, right? For conservation laws, the total mass in a system is, or the total mass is in an isolated system is constant. All right, that's conservation of mass. Momentum, mass times velocity. So it's a vector. That equation, you need to have it. That's an example there. And then remember that we can use the changing momentum as a function of time, the rate of change, to derive Newton's second law, force equals to mass times acceleration. That means that when a body, for example, when a ball is falling towards the ground and then going up again, the force applied by the ground in milliseconds, right? That force times time, which we call the impulse, gives you the change of momentum, which normally implies that, well, the collision was not ideal, was not elastic, because there is normally a change of velocity. The mass doesn't change, but the velocity changes. But that's for one object. But we also have a situation where we have collisions. For collisions, there is a conservation of momentum. That's a law that, right, in an isolated system where there is no external forces, this law always, or this is always conserved, the conservation of linear momentum. All right? In the case of planets orbiting the sun, we have the conservation of angular momentum. All right? So there is also angular momentum due to a circular motion. That's also a vector, but that's something else that we don't need to worry for now, at least. There are at least two types of collisions, actually three. There is the elastic collision and there is an inelastic collision, but the inelastic collision can be divided in two groups. The normal inelastic collision, every collision that you observe when you are playing racquetball, tennis, when you are throwing a ball, when something collides towards the ground, that's inelastic, right? Elastic is the idea of collisions not releasing any form of energy, like heat or sound or friction or thermal energy. Everything is conserved from kinetic initial to kinetic final. So we know that's not the case unless there is no friction, unless you isolate the system. So then inelastic is the most common type of collision. For problems, what we use a lot is elastic and complete or perfect inelastic. In a perfect inelastic collision, we have that a mass going and colliding against another mass. After the collision, the two masses are stick together. So the total mass of the system is the addition of the masses. And overall, they have some speed. Velocity in this case, because it's a vector, right? That's an example there, the ballistic pendulum. If you have a bullet that is traveling horizontally towards a block, a wooden block, the bullet obviously is going to be crushed inside, and it's going to stay there. But because of conservation of momentum, the pendulum is going to move towards the right. Okay? So by using conservation of momentum and obviously later conservation of energy, we can figure it out the maximum height of that pendulum that it will reach. All right? Again, we are not taking into consideration loss of heat. Now, collisions can be applied in cars, in model cars, in sports, in space, right? Engineering. So the momentum in the case of a rocket is due to the gases being ejected by the rocket, right? We also use this example to visualize Newton's third law. That's fine because yes, there is a force that is going towards the ground, and because of action-reaction, there is a reaction from the ground, per se, towards the gas and the rocket itself that helps the rocket gain momentum. But another way to understand this is by collisions, right? The momentum initial is equal to momentum final. Then we did a few of these questions. We introduced the idea of work, right? Work is the change of energy. When you are lifting something, when you are running, you are using energy. Therefore, you are performing work. Okay? So if you are lifting something, even if you're using a tool, a ramp, or in this case, a fulcrum, and any tool that you may have at home, right? It can be even a hammer. You are producing some sort of work. All right. There is also a work against the force of gravity. When you are lifting something, let's say you have your bag and you are lifting it, right, from the ground towards the table, right? You are releasing some energy, and that energy is due to the work you are using against gravity in this case. Now, obviously, that implies that there is some sort of energy, not just due to motion, but due to lifting. When you are lifting something above the ground, that's when we start talking about energy per se, in this case, potential energy. Now, the equation for work is force times distance, and the units for work are joules. However, it can also have the units of calories, or kilowatt hour, or ergs. The most common units there are joules and calories. Calories are the units that you observe in the gym when you are in the treadmill, right? It tells you how many calories you are burning by doing some work, right? So work is your change of energy, or energy is the ability to do work. All right? Remember that one thing is to lift or to push. Another thing is to carry. If you are carrying something, you're not doing any work anymore. The only work is when you are lifting the mass and you are breaking the inertia and you are giving it some acceleration up. If you are just carrying it, you are basically in equilibrium with the box, so no work done. All right? All right. Remember that we can also have this in uniform circular motion, right? In which the force acts on a moving body, but no work is done. So that's another situation where there is no work. There is acceleration, but the velocity is constant. All right? The force is always towards the center, that's centripetal force. So because it's always pointing towards the center, right? And the force is always towards the center of the circle and perpendicular to the object's velocity. So that's important. If you are, for example, in the example that I gave you when you are carrying luggage, right? If you are having your arm at an angle, not all the arm is producing work. The work is only done to the force, to the component of the force exerted that is parallel to the motion of the luggage. Because we can break forces in two directions, right? In X and Y. The perpendicular one doesn't produce any force. Only the parallel one. Okay? So that's important to know. And there are problems where they might ask you like this. The force needed to accelerate a 1,000 kilogram car from 0 to 27 in 10 seconds is 2,700 newtons. How much work is done? There are two ways of doing that, by the way. All right? You can apply energy, or you can apply the equation of work. So in that problem that you're seeing there, they found the acceleration, right? and then they use it to find the distance, and then they use it to find the force with the acceleration. And then, well, actually the force is done, the force is given. So you have the force times distance, you can get that work. How will you do it with energy? So it says the force needed to accelerate a 1,000 kilogram car from 0 to 27 meters per second in 10 seconds is 2,700 newtons. How much work is done? So let's see if we get something similar to that, or maybe the same. Here is a work energy theorem. Let's see if I get the same. 1/2 mv squared. Yeah, I get the same. Look, okay. So let me show you what I did here. Actually, sorry. Let's put the slide again. And let's share the screen. By the way, guys, the topics for the exam. So when you're watching the video today, or if you decide to go through the recording, all of these are the topics or the main sections that I'm going to be testing you guys, okay? So there it is. Anyway, so the work energy theorem is actually a very powerful tool for physics, because normally you know that there is always friction, regardless of how polished a surface can be, and no matter how much you want to reduce the friction, unless you think that anything can move forever without stopping, you know that friction eventually is going to catch up and it's going to make an object to stop, right? That means that there is always an external force. So if there is an external force acting on a body, right, then we can visualize this as having a mass, which is 1,000 kilograms in that problem. That is being pushed by a force. So in the problem, they compute work using the equation force times distance in joules. That's fine, but this started from rest. And then it came up here at 27 meters per second. The work energy theorem says that if this is the case, which is this, then the work done by the external force is equal to the change of mechanical energy. And if you remember, the mechanical energy is the addition of potential plus kinetic energy. But in this case, since the object is just in the horizontal moving towards the right, we don't have potential energy, it's always zero. So we have an energy due to this speed and an energy due to this. The energy here is zero, 1/2 mv squared, right? Kinetic energy. The kinetic energy final is the only energy. That minus zero is equal to the work done. And that's how you do it without finding acceleration and all that. So if you were to do this problem using energy, you will just say that the work is equal to 1/2 the mass times the square. And what you get exactly the same. You get 364,500 joules. That's just that. You can put here kinetic energy final minus kinetic energy initial, which was 0 joules because of this. So that problem you can just relate that. Now, in the slide, they also bring into account the fact that we have different forces, different work, right? The main one is the force due to gravity, mg. So if we introduce that force, then we can introduce, besides kinetic energy, we can start introducing the idea of potential energy, right? There. MGH. I don't like to use D because D is very generic. At least with H, you understand that is the height above the ground. Okay? So we always need a point of reference. The floor, the ground is normally our point of reference for potential energy. Okay? Can we have another point of reference? Yes. Look at the potential energy with respect to the table. Is mass times gravity times the distance from where the mass of 3 kilograms is and the top of the table. So that's important because potential energy does rely on how far you are from the reference, how high you are. Again, normally we do it with respect to the ground, but there can be cases where you can do it with respect to a table or a chair or certain height. So it needs to be clear what will be your point of reference. There can be cases where you can be below. If you are below the point of reference, that's when you start talking about, I know that the concept of negative energy is weird, but believe it or not, we do have that concept in physics, even in mechanics, even in physics 1, as you can see. But that's only the case when the object is below the point of reference. Every object, even right now yourself, you are above the surface of the, well, you are on the ground, but let's say your head is above the surface of the ground, right? If you start going underground, that's when you, theoretically speaking, you have a negative potential energy. That's because you are below the chosen reference level, because you can be clever and be like, you dig a hole in the ground, you go underneath, and then you make the reference that point under the ground. So then your potential energy is 0, and and for a person who is standing on the ground above you, the potential energy will not be 0 because it's respect to your reference point. So there are two ways of visualizing that. The main thing I want you to get out of this is the fact that for potential energy, we need a reference point. And we will do a problem on that. Okay? Now, there are other forms of potential energy. The most common one is the one that you said. Again, let's actually use the proper labels. So I want to use a board for that. We are going to be using the Hooke's law that we introduced in chapter 2. So for that, let's bring back springs. And actually, that type of energy is very commonly used in toys, in different applications, right? where you have like a spring where you want to release an object from rest. Back in the day, I remember I used to have a toy that would have a hook, and I will press the hook, and then the toy will it will be a car, it will be a car, and it will be shoot towards whatever I was pointing at. The car is at rest, and I release by pressing the device. It will release the spring, and it will make the car go towards you. So that car is gaining kinetic energy. Is gaining it from the energy of the spring. So what's the energy of the spring? The energy of the spring is the potential elastic energy. And that's the last type of energy we are going to see. Are there more? Yeah. There's thermal energy, electrical energy, but for now, in mechanics, let's just focus on, right? So when do you have, remember, a spring has a natural length. That's a natural length, the normal length. When you press, so if you compress the spring due to a force, then there is going to be an elongation. In this case, a compression X. Every spring has a constant K in newtons per meter. So the potential elastic energy is what you had on the slide. The equation is one half kx squared. There is a nice way to do this. We didn't do this, and don't worry about it, but when we did Hooke's law, remember guys, I said that if you were to plot, if you were to do, and probably you're doing this in the lab, I don't know, hopefully, because you can prove Hooke's law by doing masses, and then the spring elongates. So then you get a line. Right? This is kx, and this is your x. So a definition about this is that in a force versus distance graph, the area gives you the work. That's because a lot of these definitions, guys, come from calculus. And the area under the curve is the integral. But this one is actually not that bad, it's a triangle. So this equation is basically the height times the base divided by 2. 1/2 of the height times the base gives you this. So that's how you prove it. But in any case, that's the potential elastic. So now when we do conservation of energy, we can also have a spring. However, I don't think I will be evaluating on that. I think the main idea is the usage of it. So for example, I can give you a spring that was stretched from equilibrium a certain distance, and I ask you for the energy given the constant. That problem is also in the slides. There, application of formula, right? So that, and remember again, the equation is in joules. Now, when we talked about Newton's gravitational law, we talk about forces, but we didn't talk about energy. There is also energy related to the orbits of planets around the sun. Do you have to know much about that? No, just to know that there is. There is something called gravitational potential energy. Okay? That's normally what we call potential energy just here on Earth of a mass on top of, like, you know, MDH. But remember, guys, G, the value of gravity, can be computed, can be calculated from the gravitational constant, the mass of the planet, and the radius of the planet. So if you use that, and I think I showed you that last class, there's an equation for gravitational potential energy. All right? So just for you guys to know, and actually we can use that to explain escape velocity. When you see a rocket leaving the Earth towards the ISS, the Moon, or Mars, any missions, right? They have to break the resistance of gravity making the object come back towards the ground. In order to do that, you need to be able to overcome the gravitational potential energy of the Earth, the gravitational pull per se. So that was another addition from Newton's universal law of gravity, because we know the equation for gravitational potential energy, and we also know the kinetic energy equation, 1/2 mv squared. If we make them equals to each other, we can actually find the speed that a rocket should have to leave. Normally it's around 10 to 12 kilometers per second in the case of the Earth. Okay? And as you probably are guessing, depending on the planet, all right, for example, for Mars, the gravitational potential energy will definitely be less. Now, remember that work and energy are related. The ability to do work is energy. So for a system to be able to do work, that system must have some sort of energy. Later on in thermodynamics, we will talk about internal energy of a machine, for example, or a system. For now, in mechanics, an object to do work, it needs to have energy. For example, think about yourself. If you're going to be able to do exercise, you need to be energetic. That's why people take what? Coffee, Red Bull, right? So they get energy, or they eat, right? When you get food, you get energy, and then you can use that energy to perform work. Okay. What would be your answer for that question? Identical cars A and B are traveling down a highway with A going 2 times as fast as B. What can you say about their kinetic energies? Just remember the equation. The kinetic energy equation is 1/2 mv squared. So if one car has twice the velocity than the other car, then the other car will have 4 times, because you say 1/2 m twice v squared. Look at the whiteboard. There. That's the one for one car. For the other car, 2 squared. Oh, sorry, it will be twice. No, yeah. It will be 4 times more, because 2 squared is what? 1/2 m 4v squared. 4, there should be a 4 there, so it's 4 times larger. Okay? Okay, now we're gonna start talking about conservation of energy. That's the last bits of this set of slides. I think it's a good idea to go over that. For that, I will show you this. Let's take this away. And let's go to here. And let's show you how to do a conservation. So we talked about conservation of energy last class, but with a problem, I think it will make more sense. Let's talk about this one. You have a mass that starts at some velocity at this position, and then you want to know, well, we don't have any friction, and we want to study the conservation of energy along this. All right, so I will just do on the board that. And with this example, we will be reviewing and studying the conservation of energy. That's sort of like the roller coaster. And remember, when we are doing problems like that, we need our reference point. So look, you have the ground, and then you have like that. The height of this is 200. So this is 200 meters. This is point B. This is point A. And this is point C. And the height of this is 160. You have a mass that is going at 20 meters per second. So let's study what's going on here. The mass, as soon as you see some velocity, has some kinetic energy. And as soon as you see that the mass is above the ground, you can assume that there is potential energy. But before we calculate it, we need to put a reference, right? In an exam situation, I can ask you, point out or locate a proper reference point to solve this problem. So there are 2 points. You can put the ground, so you can say that the ground, right? You can say that the ground here can be your reference point, so you can just put here this. Like that. So you can say that all this is your reference. Or in some cases, you can make the reference point at this point. Never here. Right? It can be either there, here or here. But normally the ground is our best location. And then we can say that there is kinetic energy and there is potential energy. So we know that mechanical energy on A is equal to mechanical energy on B equals to mechanical energy on C. Mechanical energy, we're going to call it like this. Is the sum of potential energy and kinetic energy. So for A, we have both. For B, we only have kinetic energy. Since our reference is on B, or is on the ground, and B is on the ground, when the mass goes all the way up until here, it has some speed. Let's call it velocity on B. We're going to get a magnitude, right? But there is no height. So that makes the problem easy to visualize. You have that the energy on A is 1/2 the mass of the ball. You put M, you don't know the mass, times the velocity square, plus the mass of the ball times gravity times the height is equal to just the kinetic. So that's what happens in a roller coaster, right? All the kinetic plus the potential that you have on the top gets converted to just kinetic at the bottom of the ramp. Velocity on B squared. Okay, in mathematics, when the same variable is across the same atoms or factors in the equation, you can cancel it. It's a factor in common. And then we can solve this. 20 squared is 400. Divided by 2, 200. Plus, we can assume, or we can say gravity is 9.8 meters per second squared. If I multiply that times 200, I get 19.6. Yeah, that equals to 1/2 velocity on B squared. We add these two, we get 2,160 multiplied by 2, that's equal to velocity on B squared. We multiply it to the square root, and let's see what we get. We get 65.7. From 20, it jumped to 65.7 meters per second. A lot. That's why your stomach feels like you're going, it's crazy when you're in a roller coaster. For example, I think, although they actually, it's the people who developed the Kinda in Six Flags, they were very clever. That, although it's not the biggest roller coaster in the world, I think it's the biggest one in North America. The fall can be really, really bad, especially how it goes up and down too fast. So it goes like this. And by doing that, part of the energy is being transformed into, there's also rotation, and there's kinetic rotation. There's also kinetic energy due to rotation. And there's also friction, of course, right? So the feel is not as bad. The feel is not as bad. But if you go to another one like El Toro, that one feels really bad, because the height is not as bad, but it goes straight. So that one, right? So those ones, that's the best example. That's a good example for this, by the way. All right. So that's what's happening in the problem. That's conservation of energy for you guys. The slides, they go a lot into explaining this. I think this is the best way. The main thing is that there is no friction. All right, there is no friction. That's why we can assume that. And furthermore, we can also find the energy on C. Sorry, the velocity on C. But again, like a roller coaster, right? When you go up again, you lose speed. Now, do we have to use what we found? We can, but remember, the energy on A is also equals to the energy on C. So we can just use this result and make it equal to the energy on C. I will do it here. All right? So the energy for C, I will just do this. So let's see if I have this. I will put here 4C all this, which we did it here, so 200 plus 1960 is equal to not just kinetic on C, yeah, 1/2 mass, mass cancels, right? So velocity on C squared, but there is also potential energy because C is on the top there from the reference. So mass cancel, so mg times 160, right? The mass cancel because of the same as this. And there you are. So now it's just a matter of finding these factors. So we have 2160 minus 160 times 9.8 equals to 1/2 velocity on C squared, the speed on C. And then we have to use a calculator. So just in case, well, you have the calculator here on the computer, but I prefer to use the one, you know, the handheld one. If I do my math on that problem, I get 34.4 meters per second. Okay, so that's how you do that problem. Let me see here. Yeah. You don't need a mass of the particle or the block. That's the other advantage of doing this. Okay, so there you are. That's a good example of conservation of energy. Okay, in real life there is friction, so you cannot really use all of these assumptions, but it's close. It's close enough. Okay. Now there is also a couple of examples for collisions. Let me see here what we have. So we have inelastic, just applications right now on this. Let's see, we have here maybe. Oh, this one is good. Look at this one here. They give you two ice skaters, right? Suddenly push one against the other starting from rest. Stationary, that means that they were not moving. The 45 kilogram skater acquires a speed of 0.375 relative to the ice. Very important, right? Things have to be measured with respect to a stationary observer, in this case ice. What speed does the 60 km? This example actually, you can also use it in math with proportions, but let's use physics for this. So obviously, the bigger the mass, the slower the speed. That makes sense, right? When you talk about it, when you think about it, I mean, if for example you are with your kid, or playing with your cousin, or if you have a kid, right, and you're in ice and you push it, then the kid will move some distance away. But because you have more inertia, more mass, you won't move as much as your kid or the kid, right? So the way you're going to solve a problem like this is conservation of momentum. All right? When you have a situation where you are pushing or colliding or joining together, like the problem of the cars that we did last time, you have to use conservation of momentum. So conservation of momentum tells you the following. So let's do it on the board as well. Conservation of momentum tells you that the momentum initial is equal to momentum final, but you're probably thinking, well, they are not moving. So the momentum initial is 0. You are right. But remember, momentum is a vector. So you can have two kids or two people or whatever, right, standing next to each other. Like that. One is 60 kilograms. The other one is 45 kilograms. And they are not moving. So the momentum here, the initial momentum, is 0 kilograms meters second. But they push. When they push, right, one kid is moving towards the left, and the other one is moving towards the right. Since the momentums are vector, I can also say that the momentum final is 0. That's fine. That's fine. But the momentum final is this momentum plus this momentum, but this momentum is negative. So you know what happens? The way to think about it, the momentum of the person on the right is equal to the momentum of the person on the left. That's it. Because the momentum here is 0, right? It's like, for example, when you have like the rifle recoiling. When you are shooting, there is no momentum, right? You're like this. When you shoot, you do this. When you are like this, the momentum of the system is 0. But when you shoot, the bullet goes to the right. Sorry, goes to the front. But you go backwards. The addition of both momentums after you shoot the bullet is 0. But if you think about it, it's the same as saying that when you shoot the bullet, the momentum of the bullet is equal to the momentum of you and the rifle. Now, the bullet goes really fast. You only move like this. That's because you and the rifle might be around, what, 100 kilograms? More, maybe. The bullet is only, what, 5 grams? So there is a huge mass difference. That's why there is a huge speed difference. Plus, you're on the ground, so there is friction, right? Anyway, so let's talk about it here. How will you solve that problem? And the thing is that it takes more time to draw and to explain than to solve it. This, you have the masses, and they tell you that the 45 is 0.375. So this guy goes at 0.375 meters per second. So this is how you do it. You say that because momentum initial is equal to momentum final, then the momentum of person 1 is equal to the momentum of person 2. And what's the momentum of person 1? Mass times velocity. What's the momentum of person 2? Mass times velocity. That's it. Proportions. And you get the answer of that problem. Another calculator again. You get 0.25 meters per second. Okay? In the slides, you're also going to find something very important I want to show you guys here. You're going to find the idea of, oops, not this. Power. So once we talk about energy, we need to start relating it with what we work every day in daily life. You may have heard about energy ratings. Every appliance at home has an energy rating. Now, that's more to do with electrical energy, electricity, and how efficient your appliances are. Your TV, your refrigerator, your kitchen maybe, your heater, the aircon. In mechanics, any machine that is used to perform work, automatic, for example, anything that you use to lift machinery, for example, in construction or landscaping, right? It has an engine, has a motor. That motor is providing what? Not energy per se, but power. So how do we get power, or how do we get energy from power? The equation is in front of you. Power is the work per unit time, which obviously is the same as saying energy per unit time, because work is the change of energy. So we define the units of power as joules per second, which is actually called a watt. If you are lifting something in some given time, then power is equal to the work done to lift, for example, the bricks, divided by the time it takes to do it. All right? So, that's called a forklift. There you are. Okay? So that's basically power. That's how you actually measure power in real life. Remember that normally we use this unit of watts in electricity. For example, you have a 60-watt light bulb. You can have your energy rating normally comes in watts, or you have the kilowatt hour. Maybe that comes in your electricity bill, maybe it doesn't, but the idea is that kilowatt hour is basically kilojoules. No, not even kilojoules, because you have to transform hours to seconds. So it's even more than that. All right? So that's how they measure how much electricity you have used, how much power, actually how much energy, but in daily life we work more with units of power, watts, kilowatts, right? We also use horsepower. We don't really have to worry about that. The only thing I will show you on the next slide is the fact that if you're going at constant velocity, then the power can be described as force times velocity. Only, for example, if a device is performing work at constant velocity. All right? And then there is an example here where remember, we compute the amount of work right, to make a car go from 0 to 27 meters per second, right? If we have the time it took for us to do that, we can have the power. That's the power of the engine. So if, for example, let's say it takes 8 seconds for any of your cars to go from 0 to 35 miles per hour, then to compute the power, you just need to do the kinetic energy divided by the time. And that gives you the power of the engine. All right? A horsepower is equal to 746 watts. So that's how you can transform it. Again, horsepower is an imperial system unit, so we don't really use it, right? Then they put several examples of, for example, how much food is needed, how much fuel is needed for a person, for a machine, to have some sort of power output, all right? But remember, there are factors for that. There is the work and there is the time. So we can actually measure the power by knowing those factors. For example, in this case, we have that the power, they give you the power produced by they give you here the Brian Hannon Gossamer Albatross, right? So, oh, it's a propeller, right? So they tell you the time it lasted, and they give you the amount of power. So power times time, but the time has to be changed to seconds though. If you change the time to seconds, you can multiply by the power and you get the energy in joules. But the other thing that you should know is that to go from joules to calories, you need to remember 1 calorie is equal to 4.18 joules. All right? That's because that's just a conversion we get when we introduce mechanics to electricity. For example, if we want to heat water, we can compare, right? And there is a nice experiment that we can do in the lab, and normally that's the factor we get, 4.18, due to the specific heat of water. We will talk about that later as well in the course, but for now just remember that conversion. And calorie, of course, is a unit of work, right? And energy. Now, thinking about power, remember, power depends on the force and depends on the time, right? So when more people ride upward in an elevator, it requires more power. Yes, it's more weight you are carrying, right? Identical cars A and B are being driven up the same steep hill. So they are going up in a hill. If the power output of A is larger than B, what's going on? So power is work divided by time, but work depends on the force. It's the same mass and gravity, but also depends on the velocity, right? If you consider they both going at constant rate, the velocity has to be different. How different? Well, A has to be going faster than B for that to happen. All right? So in this example, it's a good way to remember that the power output is equal to force times velocity. That is in the case that you are having constant speed. Okay? I think that should be it for this. Let's see what else should we review here. Don't worry about angular momentum, all right? Until power, that's it. So everything we talked about today was about, well, here's the springs, conservation of energy, all right? Conservation of energy there, conservation of momentum in collisions, work, and momentum. and obviously potential elastic energy here. Okay. Are there any questions about the exam on Thursday?
So there's no quiz, there's just an exam?
Yeah, I think it's better if we just have the exam so we can, because it's October, and we should have at least 3 exams before the final.
Okay.
All right?
Thank you.
So it'll be your first major exam. All right, guys. So just review the information on the slides, the lectures, the problems also will help you, but I think doing the homework will help you the most because there is a lot of concepts. So for example, let's go into the homework. Let me just show you that here. The book has a lot of concepts, a lot of questions that I try to summarize in those homeworks. Right? So, energy and momentum. All right? Conceptual there. That should be pretty obvious. We're talking about conservation of momentum. Find momentum, find energy. There's a skater problem, guys. So we did it today. All right. For energy problems, because there's concepts in here, but for problems, I would recommend, if you guys did it, that's good. But remember that there are notes all the way down here. There is the kinematics notes, Newton's laws, motion, forces. Energy notes and conservation notes are important. All right. In the conservation notes, I'm pretty sure there are conservation of energy. So make sure you read that. Okay. This is a nice example because this actually, the conservation of energy shows you that if there is no friction in any of these frame, no matter what shape, the speed of the ball at the bottom will be the same. We know that that's not the case because there's always some sort of friction, right? But if there was no friction, the speed of the ball will be the same. It's sort of like the hammer and the feather, right? No matter how massive the hammer is in comparison with the feather, they both, in the moon at least, in absence of air, they will fall at the same time because of the force of gravity. So there are some examples, there it is, huh? Examples here. All right. Anyway, guys, if you have any questions, please let me know. Okay. On Thursday, we will meet at around 3:05, 3:10 to start with the exam, and it will last till 5 p.m. Okay. It won't be difficult, but there will be a couple more computational questions. Okay. Like doing some forces or work or energy. All right. Okay, guys. So I'll see you guys on Thursday then. Have a good rest of your evening.
Thank you, Professor.
See you guys. Let's stop this.